Dear students, Assalamu alaikum. This lecture is in continuation with previous lecture that we have already taken about uh, state variable description of linear time invariant systems. Okay, so somewhere we somehow we were able to uh, derive the state variable matrices and vectors and its scalar in the form of A, B, C, and D. Okay, and we said that ABC will be different. It will have different value for different for systems having different internal structure. Okay. We'll take up an example, but before that we'll mention some more things about state variable description system. Okay, so in general we say an nth order or an nth order system, it consists of at least n time shift operations. Time shift operations in its block diagram. In its block diagram. Okay. So the previous system that we have discussed, we said that it is a second order system. It is a second order system. Okay. I said that it is a second order system. That is somewhere here mentioned here. Second order system. So it is a second order system because it has two shifts. At least two shifts are present in its block diagram. Okay. So we say generally an nth order system consists of at least n time shift operations in its block diagram. It is block diagram representation. And we also say that for an nth order difference equation, okay, for an nth order difference equation, the state vector which is q of n, state vector which is q of n, will be always n by 1. Okay, it will be n by 1, n cross 1. And the matrix A will be always n cross n by n. Okay, so because the above system is a second order system, so you will see the matrix here, it is 2 cross 2, and you see its state vector is 2 cross n, because here n is equal to 2. Okay, here n is equal to 2. So that's what I'm saying, that state vector for an nth order difference equation will be n cross 1, and its matrix A will be n cross n. That will be always true. Similarly, vector B is also n by 1. Okay, it is also n by 1. And C is 1 by n. C is always 1 by n. Okay, so this is just the summary of the discussion that we had mentioned, that we discussed in our previous lecture. Now we'll take an example. This will make things, it will give you a different perspective how what is the application of these state variable description systems. So we have an example. Suppose an example like this. It says that consider the electrical circuit depicted below. Then it mentions the state variable description of system. of this. It is also mentioned that if the input is applied, if the input to the system is applied as voltage represented by x of t, and the output is actually the current. So output is the current in the form of y of t, which is through the resistor. Okay, I'll draw the diagram. So electrical circuit is shown below. That is shown here. This is the electrical circuit. We have a resistor here, and we have a capacitor somewhere here. Another resistor is here. Another capacitor is here. Okay. So it is mentioned in the question that the input is applied as voltage, which is x of t, and the output is y of t, which is actually the current through the resistor R1. Okay, so you have resistor R1, we have resistor R2, and we have voltages across these two capacitors as Q1 of t and Q2 of t. Okay, Q1 of t and Q2 of t are the voltages across the capacitor. So say for example, this is loop 1 and this is loop 2. Okay, this is loop 1 and loop 2. We have, this is a capacitor C1, this is capacitor C2, and in fact this is current I2 and this is current I1. Okay, while as Q1 of t and Q2 of t are voltages across capacitors C1 and C2 respectively. Okay, so we have to derive a state variable model, description model for the system. Okay, so how we will solve that? We'll first choose state variables. So we'll identify state variables. Since Q1 and Q2 are the intermediate quantities here, so we'll take these two as state variables. So choose state variables as the voltage across each capacitor. So across each capacitor, Q1 and Q2 are the voltages. So we'll take them as state variables. Now the second step would be summing voltage drop, that is applying KVL across the loop 1. So we will have x of t is a voltage, it will be equal to y of t is current into resistance, that will be voltage, plus q1 of t. Okay, so we are actually trying to apply in this loop, in loop 1. KVL is being applied here in loop 1, so we'll obtain this equation. If we rearrange this equation, because we have y of t as an output quantity, which is nothing but a current, it can be written as minus 1 by R1 Q1 of t, okay, Q1 of t plus 1 by R1 x of t. So let's call this equation as equation 1. Similarly, we will summing voltages or voltage drops across loop 2 also. So हम loop 2 के across whatever voltages are present, we will sum them up. Okay, so we will be able to find out in loop 2, which is the blue one. Okay, we'll be able to find out that in loop 2, Q1 of t is the voltage drop across the capacitor. It is equal to R2 into I2 of t plus Q2 of t, which is voltage drop across capacitor C2. If we rearrange them, we can find out I2 of t will be equal to 1 by R2 Q1 of t minus 1 by R2 Q2 of t. So let this equation be equation 2. Okay. However, we also know that current I2 of t is given by C dV by dt. C current through the capacitor C2 is given by C d by dt of Q2 of t, which is nothing but it is C dV by dt. Okay, it is C dV by dt. It is C dV by dt. Whereas Q2 is the voltage, so that is why we are writing dQ2 t by dt. Okay, so we also know this thing. Current I2 can be calculated by C dV by dt. If we use this, using this in equation 2, we will have this thing. D by dt of Q2 of t is equal to 1 by C2 R2 Q1 of t, okay, minus 1 by C2 R2 Q2 of t. So let this be called as equation 3. Call it as an equation 3. Okay. Now, if we apply Kirchhoff's current law at node A, what is node A? So we have node A here. We see that current y of t is equal to I1 plus I2. Current y of t is equal to I1 plus I2. So y of t is equal to I1 of t plus I2 of t. I2 of t. Uh, now, if we using equation 1 for y of t, so the value of y of t in the above equation, we will take from equation 1, y of t. Okay, equation 1 will take value of y of t from equation 1. And we will take equation 2 we will use for I2 of t. So value of I2 of t in the above equation we'll take from equation 2. And for I1 of t, we will use this equation. I1 of t, it is also known as C1 d by dt of Q1 of t. So which is nothing but I is equal to C dV by dt. Okay, it is again the same equation. So if we take values from these equations and substitute in equation A, then this is what we will be having. Okay, we'll have minus 1 by R1 from equation 1, Q1 of t plus 1 by R1 x of t on the left hand side instead of y of t. Then we will have, for I1 of t, we'll have C1 d by dt of Q1 of t. For I2, we'll have 1 by R2 Q1 of t minus 1 by R2 Q2 of t. Okay. If we rearrange above equation, we'll obtain like this. So what we'll be obtaining, we'll obtain d by dt of Q1 of t is equal to minus 1 by C1 R1 plus 1 by C1 R2 Q1 of t plus 1 by C1 R2 Q2 of t plus 1 by C1 R1 x of t. Okay, so this is what we'll be obtaining. It is C1 R2. So let us call this equation as equation 4. Now see equation 4. Now the state variable description or equation for state variable for equation 1, 3 and 4 will be written as follows. Now we can write down the state variable equation. Okay, equation 1 equation 4 and equation 3. Okay, equation 1 we can write down on the left hand side d by dt of q1 of t, d by dt of q2 of t. So this will be one vector, then it will be equal to minus 1 by c2 r1 plus minus 1 by c2 r1 is actually c1 r1 plus c1 r2. Then we have another term 1 by c1 r2. Here we have 1 by c2 r2. We have here minus 1 by c2 r2. Okay, and this will be multiplied by state variable vector q1 of t and q2 of t, plus we will have 1 by c1 r1 and 0 multiply by x of t, Okay, for equation 1 we can represent in matrix form in this fashion. Y of t will be equal to minus 1 by r 0 q1 of t divided by q1 of t and q2 of t. So this is state variable vector plus 1 by r1 into x of t. So this is the matrix form of these equations, and we can derive the state variable model. So we can see the matrix A is this R1 then by C1 2 2. So this is matrix A. Vector B is equal to 1 by C1 R1 and 0. Similarly, vector C, it is equal to 1 by R1 minus 1 by R1 then 0. Okay, and scalar D, it is equal to 1 by R1. So this is the value of A, B, C, and D for this circuit, for this system. This is actually an electrical system which is made up of 2 capacitors and 2 resistors. And we have seen the state variable description model for this system. Thank you.